Yo, welcome back, part 2. Alright, that video was getting a little long. I didn't realize how long I was talking. So we're gonna keep going. We just did Lewis dot structures. We're gonna do now geometry surrounding me. Oh yeah. We're gonna do some geometry. So the whole thing about geometry, guys, you need to learn how to count two magic things. Those two things will tell you the geometry. So, what are they? Bonding domains and non-bonding domains. So I'm going to write the definition for bonding domains first. This is just an area around the central atom that has bond parentheses S. I put that because it could be one bond, it could be two bonds, it could be a triple bond. I don't care. That's one bonding domain. Let me show you what I'm talking about. So let's say we got this little puppy right here, this little bad boy, this little molecular thing right here going on right here. So first of all, we're only focusing on the central atom, okay? I don't care about oxygen. I don't care about hydrogen. I don't care about hydrogen. All I care about is carbon. That's my friend right there. I'm gonna put a little heart. All right? That's what I'm caring about right now. How many bonding domains? This counts as one bonding domain, one bonding domain. Oh, look, there's a double bond. That counts as one only. So how many bonding domains? 3. Okay, I don't care that there's a double bond. That's one domain right there. All right, so that's bonding domains. It's just an area with bonds. The key thing to remember, single, double, triple, counts as one. Super important. If you see triple bond, like this, H, C, N. Central atom, that's what we care about only. How many bonding domains? 1, 2. 1, 2 bonding domains. Single, double, triple counts as one bonding domain. All right, y'all? So we need bonding domains. The second thing that we need, non-bonding domains. Non-bonding domains. Well, you're probably asking yourself, well, what the heck is that? Let me tell you. Non-bonding domains is lone pairs, y'all. Lone pairs around the central atom. The central atom, not the other atoms, just the central one. Just the central one. So let's go back to that other little puppy we're looking at, the same one, the same little guy. This thing's called formaldehyde, for those of y'all curious. It's called formaldehyde. It smells bad. Okay. Still looking at the central atom, so bonding domains. We already know there's 2. Non-bonding domains. What do you think? I'm going to pause it right now. Put your answer in the comments. What do you think? How many non-bonding domains? Okay. Around carbon, the central atom, guys, carbon. You guessed it, 0. 0. No lone pairs on carbon. You're already thinking, but wait, look. Oh, look right here, sir. Wait, sir. Sir. No. 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 Don't look at that one. Look at carbon. That's the central atom, okay? There's no lone pairs here. 0 non-bonding domains. Awesome. So once you get the 2 magic numbers, you look at the chart. Look at the chart. You look up for 2 bonding domains, 0 non-bonding domains. Pretend like it's a menu, like you're ordering off at a restaurant. And you say, what does that mean? Well, this one happens to be trigonal planar. And the bond angle is 120 degrees. Trigonal planar. You just read it off the table. Read it off the chart. Look at the chart, y'all. That's it. All this stuff came from right there. That's it. Let me give you another example. I didn't talk about it a lot in class, but sometimes certain things, there's certain bad boys out there who just break the rules, right? We all know them. We all know those guys. Look at this one. Sulfur. It's gonna have 6 bonds. Whoa. Can sulfur do that? Oh, heck yeah. Sulfur's a rule breaker. You got Cl, 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 you got Cl. You might be like, sir, wait. 2, 4, 6, 8, 10, 12. That's too many electrons. Yeah, I know. Sulfur's a bad boy. It breaks the rules. Boom, 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 boom. Bunch of dots here. Chlorine always has a lot of dots. Just to complete the structure, because we got to have it right. So that's what it looks like. This one, just still only look at the central atom. That's sulfur. That's sulfur. Central atom is sulfur. Central atom. Sulfur. Bonding domains. 1, 2, 3, 4, 5, 6. Whoa. 6 bonding domains. Look at that. 1, 2, 3, 4, 5, 6 on the central atom. Non-bonding domains. Do I see any lone pairs on sulfur? I only care about sulfur. I don't care about all these other his little side friends. I only care about sulfur. It's 0. It's 0. Look, sulfur doesn't have any lone pairs. It's 0. So you look at your chart, you look up 6 and 0. What do you get? Octahedral. Octahedral. What's the bond name? I don't remember because I don't have the chart next to me, but that's okay. Just look it up. That's all you do. Don't freak out if you see these. Look at it. It's just sometimes there's bad boys. They break the rules. That's okay. That's okay. You just read you do the stuff. Okay. So that is geometry. Now we're going to talk about, are you ready? Polar and nonpolar bonds. Oh, and always feel free to pause and go back, guys. And ionic. Bonds. So what I mean is a bond between any 2 atoms. So we're just looking at bonds for this part, just bonds. Remember, we got 3 types. We got nonpolar covalent, polar covalent, and ionic. These are the 3 types. How do we know what type the bond it is? Well, we have to find the difference in electronegativity. This means difference, which means subtract. This means electronegativity. Difference in electronegativity. So, there's a range for each one. What is that range? Let me tell you. Nonpolar is a small range. It's 0 to 0.4. So I'm looking for it. I gotta find this thing. I have it written down somewhere. I can't remember where I put it. Yeah, 0 to 0.4. Whoa. 0 to 0.4, right? This one is 0.5 to 1.9. Alright, this one, 2.0. And up. 2 and up. Alright? Now, why do we care about that? Well, the important thing to know here is that for, polar and, messing stuff up, I'm right. Polar and ionic they have areas that are slightly positive, slightly negative. So these have, well, let's say this. One side of the bond not pond, my bad, is slightly negative. The other is slightly positive. Alright, remember that? One side, this is only for polar and ionic, not nonpolar. One slightly negative, one slightly positive. How do you know which one's slightly negative? Slightly negative is the one that's more electronegative. Can't fit the whole word. More electronegative, meaning closer to top right corner. Corner of the periodic table, of course. And then the other end of the bond will have to be slightly positive. So for example, if you have H and F, which one of these two is more electronegative? Pause it right now. Put what you think in the comments below. Okay, yes, it is fluorine. Very good. So this one is slightly negative. This one's slightly positive, right? The other way we show this is this thing called a dipole. This is a dipole. Dipole. Di means two. Pole means like ends. There's two ends, a positive end, a negative end. This always points towards the more electronegative. The more electronegative, all right? The more negative one. That's important. We need to know that when we're doing molecules, which we're going to do right now. Let's do polar and nonpolar molecules. Polar and, look at that ampersand, that's beautiful. Nonpolar, can't spell today. Molecules. Polar and nonpolar molecules. So, how do we know if it's a polar and nonpolar molecule? Well, we got to see, are there polar bonds? And if there's polar bonds, do they make the electron symmetry? We just have to look at the electron density. So we have to look at the electron density. So, if you look at water, okay, what type of bonds are these? Put your answer in the comments below. All right, awesome. It's polar, right? These are polar bonds, which means they have a dipole. Which way does it point towards? The more electronegative. In this case, it is oxygen, right? So we have all the electrons coming up here, which means this end is slightly negative, slightly positive, slightly positive. These dipoles are pointing in the same direction, so it's almost like the whole molecule has a dipole like this. This whole bottom half is positive. This whole half is negative. Are the electrons uneven? Yes, which means it is polar. It is polar. Let's look at a different example. Carbon. Let's say we have fluorines everywhere. Each bond is polar, right? Polar covalent. So, dipole like that. Dipole like that. Dipole like that. Dipole like that. This is slightly negative. Slightly negative. Slightly negative. Slightly negative. Ooh, look at that. Everywhere around it is slightly negative. Is there any positive end? Carbon's a little bit positive, but it doesn't matter because the electron density is even. Electron density is even, which means it is non-polar. Non-polar. It's non-polar. So, is the electron density even? Non-polar. Is it uneven? That means it's polar. That means it's polar. This one you just have to practice and look at. Oh crap! You have to look at different examples. Drop my pen. We got another one. For example, you have HCN, hydrogen cyanide. This bond is non-polar. We don't worry about it. This bond is polar. So we draw the dipole like this. Slightly negative, slightly positive, right? So, is the electron density even? Do we have electrons everywhere evenly? No. This side's slightly negative, right? So that means it is polar. Awesome. Let's look at another example. Carbon, chlorine, chlorine, hydrogen, hydrogen. These bonds are nonpolar, just like up here. These bonds, however, are polar. Okay. This is slightly negative, slightly negative. But notice, we only have negativity on this side, not on this side. So we have a negative end. Carbon's a little bit positive. So that means, is the electron density even? No, we got all this here. This is here. That means it is polar. Polar, polar, polar. Good. You just have to see a lot of examples to understand this. It's just, you got to visualize it. Is the electron density even? If it is, nonpolar. Look at this one. Oops, double bond, dipole, dipole. The center's positive, but we got slightly negative here, slightly negative here. It's all even. It's all even, which means this is nonpolar. Nonpolar. Okay. Moving onwards. Intermolecular forces. So we have three types: London dispersion, forces, dipole-dipole, and hydrogen bonding. So let's get into each type. We have three types. This one we abbreviate as LDS. LDS. Let's talk about that first. LDS. So we got LDFs, London dispersion forces. This exists between temporary dipoles. So the electrons move all to one side temporarily. Here's an atom. They all move to this side. Ooh, that's a temporary dipole right there. Oh, interesting. It's temporary though, which means that these bonds are weak. Whoops. Weak. Everything has LDFs. So, in a lot of nonpolar molecules have LDFs. So, this is nonpolar / everything. Weak. So that's LDS basically in a nutshell. Dipole-dipole. Dipole-dipole. This happens between polar molecules. Is it polar? It's got a dipole-dipole. For example, let's say we got carbon. And we got this stuff going on, right? Cl. Ooh, there's a dipole like this. Nice. Slightly negative, slightly positive. Let's say we bring another one. Are they going to attract to each other? I don't know. Let's see. Are they going to be friends? Are they going to bond? Or be attracted? Let's see. Another dipole. Slightly negative. Slightly. Ooh, that's a slight positive, right? Ooh, look at that. Negative, positive. Negative, positive. This negative end, so this right here is attracted to this positive end. This thing going on right here. This is a dipole interaction. That's a dipole right there. All right, awesome. So that's dipole in a nutshell. Hydrogen bonding is a special type of dipole. This is when you have any two molecules that come together that have either an HO bond some type of HF bond or some type of HN bond. One of these. That makes a hydrogen bond, right? So let's take an example. We got, let's say, HF. Okay. Okay. Cool. This is slightly positive, slightly negative. And then let's say we got H2O, right? Slightly positive, slightly negative. These are attracted to each other. And this attraction is called hydrogen bonding. It's a really strong dipole. Strong dipole interaction. That's it. So if you see any of these going on, strong dipole. What do we need to know about this? Strong intermolecular forces means high boiling point. Also, high molecular weight means high boiling point. So, really strong forces, like hydrogen bonding, high boiling point. Really high molecular weight, high boiling point. Remember that. That's important. Okay, we're done with that. Now let's talk about chromatography. Chromatography. This is separation by polarity. Separation by polarity. The thing to remember, like dissolves. Like. Okay? So polar